guys, I'm Yashvardhan Marda. Today I'm going to be talking about electric dipoles. So, electric dipole, how do we define an electric dipole? An electric dipole can be defined by two pairs of equal and opposite charges separated by a small distance. We can call this distance 2a, and this is the definition of an electric dipole. If we are going to talk about the dipole moment is defined as the charge times the separation between the two pairs of equal and opposite charges. The direction of the dipole moment is from negative towards positive. This is the dipole moment. And this is a vector quantity. The direction is from negative to positive. That means minus q to plus q. Let us talk about the dimensions of the dipole moment. Q is the dimensions of charge is at. Dimensions of a, basically 2 has no dimension, so a is just the distance, that is length. So dimensions of the dipole moment would be Q is 80 times L. This is M0, L1, A1 and T1. These are the dimensions, and the SI unit is Q is coulomb and distance is meter, so coulomb meter. Let us see the electric field at an axial point of the electric dipole. So this is the dipole, this is minus q, this is plus q. Let's say this is A, this is B, let's say this is O, such that AO is equal to OB, and this is A, this is also A. And axial point means in the line of the dipole. Let's say this point is P. Now we need to find the electric field at the point P. So let us take the distance OP as R. So electric field on P due to this plus Q charge which is at B would be in this direction. Electric field on P due to B, and electric field on P due to A, the minus charge, would be in this direction. Electric field on P due to B is KQ upon PB whole squared, which is KQ upon PB is, this is R and this is A, so PB would be R minus A, so R minus A whole squared. Electric field on P due to A would be KQ upon PA whole squared. This is equal to KQ upon PA. This is R and this is A, so R plus A whole squared. So now the net electric field at point P is equal to electric field on P due to B minus the electric field on P due to A, because this is greater and this is lower in terms of magnitude. This is greater and this is lesser than this. So this would be KQ upon R minus A whole squared minus KQ upon R plus A whole squared. Now taking KQ as common, we get KQ 1 upon R minus A whole squared minus 1 upon R plus A whole squared. I'll just write this. this is KQ. Taking the LCM, we get R minus A whole squared, R plus A whole squared. This is R plus A whole squared, and this is R minus A whole squared. This is KQ. Now A square minus B square is A plus B into A minus B upon, now A minus B into A plus B is A square minus B square whole square. Now this is KQ. Plus A minus A gets cancelled, plus R minus R gets cancelled, so this is 2 times R times 2 times A upon R square minus A square whole square. Now this is, we know that the dipole moment is Q times 2A. So Q here and 2A here, we can replace this by P. So we get 2kpr upon R squared minus A squared whole squared. Now what if, so this was the dipole and this was the point P, this was the distance R, and this was A. Now what if R is much greater than A? That means point P is, let's say here, like at a very far distance from the point O. So in that case we can say that if R is greater, much greater than A, we can just leave A out of the equation because it will not make any much difference to the value. So this would be 2kpr upon, leaving A we would get R square whole squared, and this is just 2kp upon R cubed. R4, so R cubed. So electric field axial position, the general formula is actually, I'm not to the letter sign. The general formula is this one only. This is the general formula, and this is the special case if R is much greater than A. That means point P is at a very far away distance from point O. So the general formula is 2kpr upon R squared minus A squared whole squared, and E axial far away position, and in that case we would just leave A, so we would get 2kp upon R cubed. Second case is, let's see the electric field at an equatorial point of the electric dipole. Let's say this is minus Q, this is plus Q, this is point, let's say this is point A, this is point P, and this is the equatorial point P. The distance, let's say this is O, so AO is equal to OB is equal to A. This is A, and this distance is, let's say, R. So OP is perpendicular to AB. This is R. This is plus Q, this is minus Q. So we need to calculate the net electric field at point P due to this electric dipole, and this point P is the equatorial point of the dipole. So electric field on P due to B would be in this direction. And electric field on P due to A minus Q, so it would be in this direction. This is theta, so this is theta, that means this is also theta and this is also theta. So we will see that the sine components are the vertical components, they are getting cancelled. This is EPB sine theta and this is EPA sine theta. These two get cancelled and the cos components in fact get added up. This is EPB cos theta and EPA cos theta. So the net electric field would be just due to the cos components, not the sine components. So, and the direction of the dipole moment is from minus q to plus q charge. So the net electric field is equal to, so EPB cos theta minus p cap because the direction of the electric field, this is the electric field direction, like this is the electric field direction and this is the dipole moment direction, so they are anti-parallel, so hence the minus sign would be here. So EPB cos theta minus p cap plus EPA cos theta minus p cap, so this is just minus of EPB cos theta p cap plus EPA cos theta p cap. I took minus p cap as common, so this is EPB is KQ upon PB whole squared. This is under root r square plus a square. This is PB, so PB whole squared would be just r squared plus a squared times of cos theta. Now I write here cos theta is equal to base upon hypotenuse, so base is a and hypotenuse is this, so a divided by under root r square plus a square, so this is a upon, we can say r square plus a square whole to the power 1 by 2, and EPA cos theta would also be the same only, I'll just show, plus EPA cos theta is KQ upon PA is again the same, r square plus a square, and cos theta would also remain the same only, plus a square whole to the power 1 by 2, and this is p cap. So this is just minus of 2kqa upon r square plus a square whole to the power 3 by 2 p cap. Now again we know that the dipole moment is equal to q times 2a, so q times 2a, so replacing this we would get minus kp upon r squared plus a squared whole to the power 3 by 2 p cap. If we, for numericals we can just neglect the minus sign here. So, and one more special case in this, if the dipole, for example, if the point P is at a very far away distance from point O, that means R again, R is much greater than A, so R squared would also be much greater than A squared, so we can just leave A squared here and we would get that the electric field is equal to, this is net, this is equal to minus kp upon, we can leave a squared, so we would get r squared, a squared has been left, so whole to the power 3 by 2, so this is minus kp upon r cube, and for numericals we can leave the minus sign. So this is the general formula for the equatorial position, and this is the special case for the equatorial position if the point P is at a very far away distance from point O. So now E equatorial is equal to the general formula, we can just remove the minus sign for numerical purposes, and also the p cap because this is the vector sign, this indicates the direction. Minus here actually indicated that both of them were anti-parallel. So we can remove this and this also. So we would get Kp upon r squared plus a squared whole to the power 3 by 2, and E equatorial for far away would be Kp upon r cube. Yeah. Now if we study all these four formulas together to just get a much better understanding, this is the dipole, minus q plus q, this is point A, this is point B, this is point O, this is A, this is A, this is point B, this distance is R. So if the point was here, we would use the formula as the electric field, this formula, 2 kpr upon r squared minus a squared whole squared. If the point P was at a very far away distance, let's say here, we would use this formula. At this point we would get electric field is equal to 2 kp upon r cubed. If the point P was, let's say, here, and this was, let's say, r, so for this case we would use this formula, equatorial formula, Kp upon r squared plus a squared whole to the power 3 by 2. If the point P was at a very far away distance, let's say here, then we would use the far away formula, which is Kp upon r cube. We can also see that E axial far away is equal to twice E equatorial far away. 2 kp r cube and kp upon r cube. So E axial far away is twice of E equatorial far away. Now let's see this. If this is the electric field and this is our dipole, this is, let's say, plus q, and let's say this is minus q. So the force exerted on this point would be in the direction of the electric field, and this force would be equal to plus QE. The force exerted on this point would be opposite, so this is minus QE. The distance between the electric dipoles we know is 2a. If this is theta, so this would be 2a sine theta. If we were to find the torque, we know that torque is equal to force times the product of the perpendicular distance. So this is, force is qa times the perpendicular distance, not this distance, the perpendicular distance, which is 2a sine theta. And we know that P is equal to q times 2a. So replacing this, we would get torque is equal to Pe sine theta, or torque is equal to P cross E in this case. Now let's talk about some special cases again. This is the electric field, and this is, suppose our dipole is kept like this. This is minus q, this is plus q. Direction of electric field is from left to right, and direction of the dipole moment is also from left to right. This would be plus QE and this would be minus QE. So basically F net would be QE minus QE, which is equal to 0, and tau net would be, since sine theta is basically the angle between P and E. So since P, dipole moment and electric field are in the same direction, theta here would be 0. So if we plug in theta is equal to 0, sine 0 is just 0, so tau net would also be 0. This is for theta is equal to 0 degrees, and this is a case of stable equilibrium. So the second case, this is the electric field, and suppose our dipole is kept like this. This is plus q and this is minus q. This is QE plus and this would be minus QE. So again F net here would be QE minus QE, which is equal to 0. The direction of the electric field is from left to right, but the direction of the dipole moment is from minus to plus q, so from right to left, like this. So in this case theta is 180 degrees because the angle between the electric field and the dipole moment is 180 degrees. They are anti-parallel. So if theta is equal to 180 degrees, again sine 180 is 0, so tau net would again be 0. This is for theta is equal to 180 degrees, and this is a case of unstable equilibrium. If this is our electric field, and suppose the dipole is kept like this, this is plus q, this is minus q. Force on this point would be in this direction, QE plus, and this would be minus QE. So F net in this case would be 0 again, QE minus QE, which is 0. Tau net would be, so basically here the direction of the dipole moment is from minus to plus, so it's like this, and electric field is like this. So this is dipole moment and this is the electric field. So this is 90 degrees. Theta is equal to 90 degrees. So for this, if sine theta is equal to sine 90, so we would get tau net is equal to PE. This is for theta is equal to 90 degree, and this is a case of, so only translational equilibrium is achieved. Translational equilibrium means basically linear equilibrium, you can say, and rotational equilibrium is not achieved because tau net is not equal to 0. So translational equilibrium is achieved, but rotational equilibrium is not achieved. That is all for electric dipoles. I hope you all enjoyed this video. Please like, share, comment and subscribe to my YouTube channel. Also feel free to drop your doubts in the comment section, and I'll see you all in the next one. Thank you.